So today we're going to start talking about trusses as part of our structural analysis. This is really going to be taking like our equilibrium equations that we've been working on and use it in this real-world application of trusses. And you're probably familiar with them. Maybe you did some kind of project in high school where you built a truss to see how much weight it could withstand before it would break. That's usually a really common engineering thing you do in high school sometimes. And trusses are used all the time in the real world. I mean, especially in structural, but they work really, really well as this support system, right? So forces are applied to these trusses, and we want to see how they're going to react and how they're going to respond to these forces. Most of the time, these problems we do work in 2D, so there isn't going to be any 3D in this unit, and that's because in real life, that's typically how we simplify a truss. Even if we have something like a bridge, you know, if our little truss, my truss is looking a little more like a croissant here, but my truss, if it goes backwards, it's usually two of the same truss side by side with these joints between at these joint locations. These joint locations, which is where we usually see the loading on a truss. So when we see these things, usually we say, all right, there's a load here and a load here, you know, maybe a load here, something like that. When we're doing with these, it makes the most sense to simplify these down to a 2D system. And there are a few assumptions that we make when we're working with these trusses. So one is that we're going to assume that every single one of these little spans of the truss is a 2-force member. And what that means is that none of the loading is going to be applied at the joints of these members, and instead, for each member that we have here, it's either going to be in tension or my member is going to be in compression. All right, so either the forces are acting on the beam compressing the member, or it's going to be in tension. Forces are going to be pulling on the member. Sometimes we do have 0-force members. We're going to talk about that in the next video, but generally we say all of our members only have 2 forces. They're 2-force members. No load is going to be applied anywhere on the member itself, only on the joints. So these members are going to be in tension or compression. Any loading is going to happen on these joints and not anywhere on the body of the member itself. And that every connection at these joints, every one of these connections, is going to be a pinned connection. So every joint here, every location where the members come together are going to be pinned locations. So they could have, they allow for rotational movement, right? There's no moment constriction, but they're constricted in the X and Y directions, as our pins normally are. They're constricted in the X and Y, but allow for rotational movement. And finally, we're just going to say that the weight of the truss itself is negligible for the purposes of learning how these trusses work. And again, generally, all of the load of these are applied to the joints, so even the weights of the members are probably very, very small compared to how much we're going to be loading on a truss. Now, when we analyze a truss, we typically do this with our equilibrium equation. There are really 2 main methods to use when analyzing a truss, and this is the method of joints and the method of sections. In this video, we're going to go over method of joints, and we'll do method of sections in another video. But both of these are ways to find out what the forces are through each member. And a member, again, is just these beam locations. So here I have a member between A and C. We would call this member AC. We typically name it by the points it goes between. So this lower one would be member AC. On this side, this connection beam here would be member AB. And then this diagonal connecting them would be member BC. And this would be just a super, super simple truss. It's sitting on a pin at A and on a roller connection at C. So this would be a very, like, the most basic form of truss you could get is a triangle. So this is the most basic truss you would be seeing. It has the 3 support reactions for stability. And basically we use this to find out what the force is through each member. So we have a procedure for analyzing this with method of joints. And your first step is going to be to draw a free body diagram for the entire truss itself. So no matter how big your truss is, you can simplify it to kind of like the external shape of your truss, and then you can analyze all of the reactions on that just as you would for like a normal equilibrium problem. So for this one, I'll go ahead and draw it over in yellow next door. So I'm going to draw them just as simple lines, just the outer lines. There are no inner lines in this truss anyway, but I would draw probably just the outer lines here. I would put on my applied forces that I see. So I see a 500 Newton applied force to the right at point B, and then my reaction forces. So I have a pin at A, so I'm going to have a Y reaction force and an X reaction force. And then I also at C have a roller, so I'm going to have a Y reaction force at C. So now that I have this free body diagram, my next step is to apply the equilibrium equations and solve for these reactions. So solve for reactions with our equilibrium equations. Solve for our reactions with our equilibrium equations. So these, of course, are our sum of x forces, sum of y forces, and sum of moments equals 0. So in this case, I would start with my moment, usually the easiest thing to start with. I'm going to go ahead and take a... Whoa! Sorry. I'm going to go ahead and start with my moment. That's the easiest thing to start with. Take a moment about A equals 0. Of course, it's in equilibrium. It's not going anywhere. I'm going to take a moment about A. That means my A forces don't count here. And I'm just going to have the Cy and the 500 Newton force. So that's going to equal negative 500 times the 2 meter distance that was given in our original prompt here. 2 meter distance plus Cy also at a 2 meter distance times 2. So easy enough. That just gives me that Cy is 500. Cy is 500 newtons, and I assumed the correct direction. It ended up positive, so it is in fact pointing up as I drew. And then of course, from this it's pretty easy to tell even without setting up the equilibrium equations. You can intuitively tell, alright, the only x forces I have are Ax and the 500, so Ax equals 500, and then the only y forces I have are Ay and Cy. If Cy is 500, then Ay is 500. So it worked out extremely simply in this one, that with all of my equilibrium equations, even if I say sum of x forces is 0, which is negative Ax plus 500, I have my Ax support reaction is 500 to the left, and same if I do my sum for Fy. If I just write out the math here, get Cy plus Ay, which means I assumed the wrong direction for Ay, because my Ay will end up negative. So Ay is 500 newtons pointing downward. And these are my support reactions. So this is just the same as the equilibrium problems we've been doing so far. But now we have these added steps in solving what are the forces going through the members. So now that we have those equilibrium reactions, we've solved for the reactions, it's typically not what we're looking for. We're looking for the forces in the members themselves. So to do that, we're going to look at every joint, treating every joint like a single point, and making a free body diagram of each joint, of each point. So the third step is to draw another free body diagram, but now at a joint. At a joint. And you want to do this at a joint where you don't have more than two unknowns, because we're only going to have two equilibrium equations in this case. Since we're looking at a single point, we're only going to have our forces in the x direction and forces in the y direction. At a single point, there isn't going to be a moment that we can take. So just to continue looking kind of at this example, is if we look at joint A that we had just solved for, so let's say, okay, so at joint A, if I draw what we just solved for the reactions at A, so I have this 500 Newton force that points downwards that we just solved for, and then AX we said was 500 to the left. But now we're going to include these member forces, which I'm going to label as AB and AC. So AB being the force through member AB, that's the force through this member on the left side, and then member AC is the bottom member here. It's the force through that member. These arrows pointing away from the joint indicate that it is in tension. Tension. If my arrows point away from the joint, if my arrows point towards the joint, it indicates that that member is in compression. So it is being squished, whereas in tension, it's being held taut, pulling away from itself. So tension arrows point away from the joint, and this is the way we usually assume members are until proven otherwise. So we usually assume a member is in tension, and then we do the math and see if it comes out negative, then it's actually in compression. So in tension always acts away from the joint. So both of these being in tension, we can solve this now, right? It's pretty straightforward to solve. If you had any angles, you apply your equilibrium equations. Your sum of x equals 0, sum of y equals 0. Right, that's step 4. Step 4 here is after you draw a free body diagram at the joint itself, you solve for the member forces. Again, this is why you don't want more than two unknowns at a joint. So pick a joint strategically. You're going to have to go through multiple joints likely to find all of the member forces, because we can see in this one, we still aren't going to be able to solve what BC is. So we're going to have to go to another joint after this. But in this case, we are through the free body diagram for A. We are going to solve for our member forces, again using the equilibrium equation. So in this case, it's pretty straightforward to see that AB is going to be 500 and AC is going to be 500, right? They're all pointing in directly opposite directions. We really don't have to apply the equilibrium equations. They just kind of intuitively make sense to us now. That, all right, every force is 500, right? They're pointing in opposite directions. Equal and opposite gives you a balance. Write that here. So my AB is 500 newtons, and it's drawn correctly, right? So it is in tension. And we usually do this by marking. Let me give me a little more space here. We always mark whether our members are in tension or compression by putting a C or a T afterwards. So in this case, AB equals 500 newtons, and that is in tension. Usually we just put that in parentheses right afterwards to indicate the force on that member being in tension or compression. In this case, they are both in tension because both are pointing away from the joint. So that's 2 of my 3 members. Now I have a choice to make, right? So the last step of this process is essentially just repeat steps 3 and 4 until you've solved for every single member of your truss. So you just keep repeating steps 3 and 4 until everything is solved. We are going to have to repeat it because at point A, we only had 2 of the members and not the 3rd. But you do have a choice here. You can choose whether you want to do it at point B or at point C. It'll work out the exact same either way. So it's up to you which you feel kind of more comfortable with. I'll show both setups here. So again, you would just do, I'm gonna move, get rid of this guy. So again, you're going to draw your free body diagram at your point of interest. So at point B, my free body diagram has the force through AB, which we already solved. It's 500 newtons. That's 500 newtons. It has that 500 newton force that was applied. Right, that's this force here that was given. And then it has our unknown. So at this 45-degree angle, the force through BC. So you can do this at point C or at point B. Either one is going to work out. Right, so if I did it at point C, I would get CY, which we calculated again is 500 newtons. Right, we found that over here. CY is 500 newtons acting upwards. BC, again, assuming in tension, pointing away from the joint. Right? So BC, depending on whether you look at B or C, they're pointing in opposite directions, but they're both pointing away from the joint that they're acting on, showing that it's in tension. So BC in tension, and then AC, which again, we found this was 500 newtons. So when I set this up, in either case here, I would apply my equilibrium equation. Right? My sum of forces in the y direction equals 0, sum of forces in the x direction equals 0. And what I'm going to get is that BC is negative 707 newtons. Negative 707 newtons, which means that my direction was wrong. It is not pointing this way. It is actually in compression. It is pointing out this way. So we would write 707 newtons in compression. And that would be it. Now that I've solved for every member of the truss, in this case the 3 members, my problem is complete, and my final answer would be all of these forces, the lists of forces through every member. Let's take a look at another example. So here I want to determine the force in each member of, again, a very simple truss. Now I have 1, 2, 3, 4, 5 members, AB, AD, BD, BC, and CD. I have 5 members, a pinned connection, a roller connection, and then a 400 Newton and 600 applied force on this truss. So again, I'm going to follow the exact same steps, which is look at the truss as a whole, set up its free body diagram, and find the reactions. That is like the first set of steps. And then our second set of steps will be finding the forces in each member by looking at each joint. So each of the 4 joints that we have are going to have all 5 of those connections. So let's go ahead and do the first part, right? Just the solving for our reactions. Set up and solve our reactions. So if I draw my free body diagram here, now I don't have to have this member. This member BD is not necessary. It's not necessary You can keep it if you like, but we're just looking at the overall shape of the truss as we're setting up to solve for our reactions. So I have 400 Newton and 600 Newton applied forces. And then at my pin, I'm going to have an X and a Y. Right, so here at point C, here's a CX reaction. And here is a CY reaction. And then at point A, I have the roller, so just a Y reaction. AY. So now that I have this, I'll apply my equilibrium equations to solve for each of those reactions. So I take a moment about point C. Again, you can take a moment about anywhere. This is just the easiest one to get rid of a lot of the forces, right? Get rid of the unknown C forces. I'm going to have my 400 Newton force times the 3 meter distance away, right, this 3 meter distance, minus AY, because it is going clockwise around C, times the 6 meter distance away. And then finally, we have that 600 Newton applied force plus 600 times that 4 meter distance below the pin. So I punch the algebra into my calculator, and I get that my AY reaction is 600 newtons. 600 newtons. And I assumed correctly. It is going up. 600 newtons up. I'll go ahead and do my Y reactions. Since I just found what AY was, I know that AY is 600 minus the 400 applied Newton force minus CY. So pretty simple. I get CY is 200 newtons. And again, I assumed the correct direction. So it is pointing down. And then finally, my Fx, which I could have done first. Again, it's your choice, what order you do these equilibrium equations in, is negative Cx plus 600. So nice. I assumed the correct direction on all of these. Just by happenstance. I got Cx is 600 newtons pointing to the left. So don't let it deceive you that just because it's you get a positive number that it's not pointing to the left, because that's the negative x direction. It just means I assumed the direction correctly, that it is in fact pointing to the left. So that's the first half of solving our truss, right? Just getting our reactions so that we can apply them to each joint as we go through our joints, right? Because you might be tempted to skip the reaction part and just say, okay, I'm just gonna, there's no reactions at B, I'll just solve at point B. But if you tried to do that, and you tried to make your free body diagram at point B, you have 3 unknowns, right? BC, BD, and BA. So here we couldn't solve for the reaction. There are too many unknowns. Oh, there's also, even with this 400 Newton applied force, there are only 2 equilibrium equations we can apply on these joints, right? The force in the y direction and the force in x direction, the summation of those. So instead, we'll want to start with a joint with 2 unknowns. And that can be up to you. We know it can't be B, and we know it can't be D. Both of those have 3 unknowns. But at point A, we only have 2 members coming off of it, 2 unknowns, AB and AD. Or we can choose point C, which has BC and BD. Whichever way you choose is going to work out just fine. It is totally up to you and how you think about solving the problem. But you can start at either one of those. So for me, I'm going to start at point A because when I analyze these, I typically just go from left to right. That's usually how I read them, so that's how I tend to solve problems, is just going down the line left to right to make sure I haven't missed anything. So I would start at point A. So at my point A, I know I have member AB, the tension force from member AB. I have tension force in AD, and then I have AY, that reaction force. That reaction force AY, which we said was 600 newtons pointing upwards. So now I can apply my equilibrium equations to solve for AB and AD, right? Now you'll notice this here, even though no angle was given, I have a 3 meters, a 4 meters, making this a 3, 4, 5 triangle. So when I set up my equilibrium equations, my forces in the y direction equals 0, going to be 600 plus 4/5. 4/5 AB. And no AD, it's entirely in the x direction, right? So here I can see that, again, my direction is assumed wrong. I assumed it was in tension, but actually, I get a negative number for AB. I get negative 750. Which means when I write this, what I want to write is 750 in compression. 750 newtons in compression. So that's 1 down, 4 more members to go. Do my equilibrium equation equals 0 equals... Now I know. Now that I know AB is negative 750, it's pointing the opposite direction, I can go ahead and include that assumption in my x equilibrium setup, or I can choose not to and it'll work itself out, because I'm going to have to plug in that 750 for AB anyways. But I'm going to go ahead and assume that it's the negative 750. I'm going to plug that in here. The negative 750 times 3/5, right? That's the x component of AB. 3/5 times negative 750 plus AD. So that gives me that AD is going to be 450 newtons in tension. Right? Since that AB was negative, our AD ended up working out positive. Okay, not bad. 2 members down and 3 more to go. So now you're going to have to make a choice, because you can use any of the joints, right? Now at B, there are 2 unknowns since we solved for AB, and at D, there are also 2 unknowns. We solved for AD. But again, you could also just go back to point C if you wanted to. So it is totally up to you what method, which joint you wanna move on to. For me, I'll do point D. Again, not that it matters. It's all gonna shake out. I'll move those reactions. I don't need them. But I do want to keep my answers here, so I'm gonna look at point D now. Do my diagram for this. I have the applied 600 newtons. I just solved for AD. So we said this was 450 in tension. And then I have my 2 unknowns. So the direct up DC and the 3, 4, 5 triangle of BD. So that's my free body diagram of point D. And again, I just keep repeating this for joints, walking on down the line until I have every single member solved. So again, I want to do my sum of my forces. I'll do x direction this time. So I have 600 minus 450 minus the x component of BD, 3/5 BD. So my answer is going to work out to be positive. So I assumed the correct direction. BD is in tension. 250 newtons. 250 newtons in tension. My next equilibrium equation, Fy, is going to be just my CD component plus the y component of BD. 4/5 times 250. So my CD is going to end up negative. I'm going to get negative 200 newtons for CD, so it is in compression. CD is 200 newtons in compression. So I have 4 of my 5 members, which means I'm going to have to do an equilibrium at one more joint. I can pick B or C. Those are the only 2 joints that are left that I haven't analyzed. So if I look at C, again, either one is fine. I have my reactions from C, we said, were 200 newtons downward and 600 newtons to the left. And then I have from member CD, I have, again, 200 newtons. And then I have BC. Now note again that the 200 newtons from CD is pointing towards the joint instead of away from the joint because it's in compression. Right? This is in compression. Put a C next to it. Compression. But BC I drew away from the joint because I'm assuming that it's in tension. And I'm going to be wrong. I can see that I can't have my 600 and my BC pointing in the same direction and have them be in equilibrium. So my BC is going to be in compression as well, right? BC should actually be pointing this way. To be in equilibrium, if I do my sum of forces in the x direction equals 0, I would have negative 600 minus BC. My BC would be negative. So BC is 600 newtons in compression. And that's it. Now I have the force in all 5 of those members, and I can tell how much loading they're taking on. This is very good, very very applicable in the real world, especially when we start talking about things like failure and how much load something can have. We would really want to know which one of these members is going to fail first, or which one of these members might be their failure, which one is taking on the most load, if there needs to be more supports somewhere else. So this is very important for us to know how much each member of a truss is taking on and what forces each is experiencing.